Welcome to the CosmoX channel. At this very moment, the fastest spacecraft ever built by humanity is traveling at 61 kilometers per second, and yet, it would need 70,000 years to reach the nearest star. And that is not even our biggest problem. Tonight we are going to delve into a question that has tormented humanity since the moment we raised our eyes to the starry sky for the first time. A seemingly simple question, but with a devastating answer. What is the reason why it is impossible for us to venture beyond the limits of our solar system? We are not talking about technological deficiencies or budgetary restrictions. We are talking about something much deeper, much more definitive. The basic rules that govern the cosmos seem to have erected a transparent prison around us. A wall that no amount of human creativity will be able to tear down. When this journey ends, you will understand precisely why we find ourselves locked in this minuscule fragment of the universe, perhaps eternally. Before starting, if this style of historical and profound content captures your attention, a like or a subscription contributes immensely to the development of the channel. It's a modest gesture, but it represents an enormous impact for this project. Now yes, let's begin this journey. Let's start with something you surely know, but whose true scale you rarely manage to grasp. The closest star to our Sun is Proxima Centauri, a red dwarf star, tiny and dim, located about 4.24 light-years from us. When we mention light-years, we refer to the distance that light travels during an entire year, moving at 300,000 kilometers every second. That equals approximately 9.46 trillion kilometers for each light-year. Proxima Centauri is located at 4.24 of those distance measurements, which represents about 40 trillion kilometers. Write it this way, 40,000 billion kilometers. 40 trillion. This figure is so immense that the human brain simply cannot assimilate it in a real way. Let's try to make it more understandable. The fastest space probe that humanity has manufactured is the Parker Solar Probe, created to investigate the Sun. At its maximum capacity, it reaches about 700,000 kilometers per hour when it approaches the Sun. That is an extraordinary speed, superior to anything we have developed. But even at that impressive speed, it would need more than 6,500 years to reach Proxima Centauri. Reflect on that for a moment. 6,500 years. When that probe finally arrived, more time would have elapsed than has passed since the construction of the first Egyptian pyramids. The entire record of documented human civilization from ancient Sumeria to today would fit within the journey period, and there would still be millennia left to arrive. And that is only to the nearest star. The Milky Way, our galactic home, has approximately 100,000 light-years in diameter. It houses between 100 billion and 400 billion stars. If we wanted to cross the galaxy from end to end traveling at the speed of the Parker Solar Probe, it would require approximately 150 million years. 150 million years. The dinosaurs disappeared 66 million years ago. Could you undertake that journey when the dinosaurs still reigned on Earth? Travel through their entire era, their disappearance, the birth of mammals, the evolution of primates, the appearance of humans, all of documented human history, and you would still be halfway to your destination. We are not talking about distances that exceed our present technology. We are talking about distances that surpass biological, geological timescales, even beyond the scales at which species evolve. But perhaps you believe that this is merely a matter of speed. If we manage to manufacture faster ships, if we manage to approach the speed of light, perhaps then it would be viable. After all, light travels from Proxima Centauri to here in only 4.24 years. If we manage to move at 10% of the speed of light, we would arrive in 42 years. A complete human existence, correct, but achievable. A young person could leave Earth and reach Proxima Centauri as an elderly person. Complicated, yes, but not unattainable. This is where reality begins to reveal its most merciless restrictions to us. Achieving 10% of the speed of light, 30,000 kilometers per second, is not merely complicated with our present technology. It could be fundamentally unattainable for any crewed ship, no matter how developed our technology may be. Let's talk about energy. The energy required to accelerate an object increases dramatically as you approach the speed of light. This is not a technological restriction, it is a fundamental law of physics described by Einstein's special relativity. As an object moves faster, its effective mass increases. The faster it goes, the more energy is required to accelerate it even more. At speeds close to light, the amount of energy needed becomes absurdly enormous. Let's do some rough calculations. Suppose we want to send a ship that weighs 1,000 tons, approximately the mass of the International Space Station, to 10% of the speed of light. The kinetic energy needed would be approximately 4.5 times 10 to the 20th joules. To put it in perspective, that is approximately the total energy consumption of all human civilization for several years. All the electricity produced by every power plant on the planet, every drop of fuel consumed, every solar panel, every wind turbine operating continuously for years, just to accelerate a ship to 10% of the speed of light. And that is only the energy to accelerate. You also need to decelerate when you reach your destination, which demands approximately the same amount of energy. So, you're really looking at double that amount, and this assumes perfect efficiency, that every joule of energy you produce goes directly to accelerating the ship without losses. In practice, no system is perfectly efficient. Conventional rocket engines have efficiencies of only a few percent. Even the most efficient theoretical systems we can conceive might have efficiencies of 50 to 70% at most. This means that the actual amount of energy you would need to produce would be several times higher. So, where would we get all that energy? Conventional chemical thrusters are useless. Chemical fuels lack the necessary energy density per unit of mass. If you intended to use chemical thrusters to approach even a relevant fraction of light speed, the mass of fuel required would be enormous. In reality, the numbers show that no matter how much fuel you load, it would never be enough to achieve such speeds. The mass of fuel expands exponentially as the target speed increases, and soon you reach a threshold where you would require more fuel than the combined mass of entire planets. Chemical thrusters transported us to the moon, enabled us to send probes throughout the solar system, but they are absolutely useless for interstellar journeys. What about atomic propulsion? Atomic fission releases about 1 million times more energy per unit of mass compared to chemical reactions. A fission reactor fragments heavy nuclei like uranium or plutonium, releasing energy during the process. Atomic fission thrusters have been proposed for decades. Project Orion, conceived during the 50s and 60s, proposed using atomic detonations to propel a spacecraft. Fundamentally, you would activate atomic charges behind the spacecraft and the shock wave would propel the spacecraft forward. It seems risky and impractical, and it is, but numerically it could work. Projections indicate that an Orion thruster could achieve speeds up to 5% of light speed, possibly up to 10% with very optimized configurations. That surpasses chemical thrusters, but you're still looking at journeys of 40 to 80 years to Proxima Centauri. And that represents only the nearest star. Project Orion never materialized, partially due to international agreements that banned atomic weapons in space, but also due to colossal engineering obstacles. You would need thousands of atomic devices, each detonating in perfect temporal coordination. You would need shock-absorbing shielding resistant enough to withstand repeated atomic explosions, and you would need to safeguard the crew from radiation. These obstacles are not theoretically insurmountable, but they are exceptionally complex. Even if you manage to overcome all these obstacles, you remain restricted by the amount of fissionable material you can load. Atomic fission has restrictions regarding how much energy it can generate per unit of mass. So, what about fusion? Atomic fusion, the mechanism that energizes stars, could supply superior amounts of energy. Fusion unites light nuclei, generally hydrogen, forming more massive nuclei like helium, releasing colossal amounts of energy. Fusion represents the ultimate goal of terrestrial energy generation. We have attempted to develop viable fusion reactors for decades, and despite having achieved progress, we still lack an operational fusion facility that generates more energy than it absorbs. But let's imagine that we master fusion. Let's imagine that we develop effective fusion thrusters for spacecraft. How much would that benefit us? Projections indicate that fusion thrusters could theoretically accelerate a spacecraft up to 10 or perhaps up to 20% of light speed. That would compress the journey period to Proxima Centauri to 20 or 30 years. It's still a complete human existence, but it's beginning to look attainable. You could send young crew members and they would arrive as mature adults or elderly people. The inconvenience lies in the fact that developing a fusion thruster for a spacecraft is considerably more complex than developing one for a fixed energy facility on Earth. On Earth, you can have colossal and massive reactors with gigantic electromagnetic fields to confine the plasma. In space, every gram matters. You require a light thruster, reduced in size and capable of generating thrust for years or decades uninterruptedly. You require fusion fuel, surely deuterium and helium-3, which are scarce and complicated to obtain in considerable volumes, and you require managing the tremendous heat generated by fusion reactions. You cannot merely radiate heat into the space vacuum as simply as you might suppose. The vacuum functions as an excellent insulator. The heat sinks required to eliminate the heat from a fusion thruster would be enormous and massive. Even overcoming all these impediments, we still face another elementary inconvenience: fuel. A fusion thruster must carry its fuel. Contrary to an airplane that can refuel, an interstellar spacecraft lacks refueling stations during the journey. You must carry all your fuel initially, and the more fuel you carry, the more massive your spacecraft becomes, implying that you require superior amounts of fuel to accelerate it. This inconvenience, called Tsiolkovsky's rocket equation, establishes an elementary barrier on how much speed you can achieve based on how much fuel you can carry. To achieve truly elevated speeds, an immense portion of your spacecraft's mass must consist of fuel. At near-relativistic speeds, practically all of your spacecraft's mass would be fuel, leaving minimal space for the practical payload, the crew, the life support systems, and the spacecraft's instrumentation. Here arises a seemingly astute proposal. What if we avoid carrying the fuel? What if we capture it during the journey? This concept is called the Bussard ramjet, proposed by scientist Robert Bussard in 1960. The concept proposes using a colossal electromagnetic field to capture hydrogen from the interstellar medium, the dispersed gas existing between the stars. Subsequently, you use that hydrogen as fuel for a fusion thruster. Theoretically, as long as hydrogen exists in space, your spacecraft could continue accelerating eternally. You would never exhaust the fuel because you capture it continuously. Sounds ideal, correct? The inconvenience lies in the fact that interstellar space is incredibly unpopulated. The average density of the interstellar medium is approximately 1 hydrogen nucleus per cubic centimeter. That represents 1,000 trillion times lower density than the most perfect vacuum we manage to generate on Earth. To capture sufficient hydrogen and feed a fusion thruster, you would require an absolutely colossal electromagnetic collector, surely thousands of kilometers in diameter. The mass of the electromagnets and the equipment required to produce such an enormous electromagnetic field would be tremendous. And as you accelerate, the resistance caused by capturing all that hydrogen could slow you down more than the thruster propels you. Projections indicate that Bussard ramjets could be inoperable with realistic densities of the interstellar medium. It's a theoretically beautiful proposal, but practically unattainable to materialize. So, fusion, even in the most favorable scenario, only transports us to speeds of 10 to 20% of light speed. And that presupposes that we master colossal engineering obstacles that we have not yet overcome. What about going faster? What about approaching light speed? This is where physics becomes truly implacable. Antimatter represents the substance with the highest energy density that we know. When matter and antimatter meet, they annihilate totally, transforming 100% of their mass into energy, according to Einstein's famous equation equals mc squared. No other mechanism we know is as effective. If we manage to use antimatter as fuel, we could theoretically propel spacecraft at speeds extremely close to light speed, perhaps 90% or even higher. The inconvenience lies in the fact that antimatter does not exist naturally in usable quantities. We must generate it in particle accelerators, and it is absurdly expensive and complicated to produce. CERN, the most enormous particle physics laboratory in the world, generates only a few nanograms of antimatter annually. A nanogram represents 1/1,000,000th of a gram. To fuel a spacecraft, you would require kilograms or even tons of antimatter. With present generation rates, it would require billions of years to generate such a quantity. Even if we managed to generate antimatter massively, storing it would be incredibly complicated. Antimatter annihilates instantly upon contacting normal matter, so you require storing it in electromagnetic or electric traps that prevent it from contacting the walls of any container. These traps demand energy to operate, and any malfunction would result in a colossal detonation. Subsequently, there is the inconvenience of using antimatter as propulsion. When matter and antimatter annihilate, they generate mainly gamma rays, photons of extremely high energy. Gamma rays are extremely difficult to direct or use for thrust. Most of the energy simply disperses in all directions, without propelling your spacecraft forward. Transforming antimatter annihilations into usable thrust constitutes another enormous engineering obstacle. Even with antimatter, you would surely be restricted to speeds around 50 to 90% of light speed as a limit. Now, at speeds truly close to light speed, let's say 90% or higher, the phenomena of special relativity becomes significant. Time dilates for travelers. If you move at 90% of light speed, time for you passes more slowly than for people on Earth. A journey of 10 years according to Earth clocks could be experienced as only 4 or 5 years for you. This is authentic, it does not constitute science fiction. The clocks on spacecraft would truly operate more slowly. At even higher speeds, let's say 99.9% of light speed, temporal dilation becomes extreme. You could travel for decades or centuries according to Earth clocks, but for you it could be experienced as only a few years. This could make prolonged interstellar journeys more tolerable for the crew. You could travel toward distant stars without aging considerably. But there is a trap. While you experience only a few years, everyone on Earth ages normally. You return home after what seems like a 5-year journey, but on Earth 50 or 100 years have passed. Everyone you knew is deceased. Society has mutated unrecognizably. You are a time traveler launched into the future with no way to go back. This poses a profound philosophical question. Does this truly constitute a round-trip journey? Physically, yes, you can return to the same planet, but in all significant senses, the Earth you return to constitutes a different place. You cannot reunite with friends or family. You cannot share your experiences with the people who said goodbye to you. You are a stranger from your own future. This transforms interstellar travel into permanent exile. Once you leave, you never truly return home. This does not constitute a technical restriction, it is an elementary consequence of how space-time operates. Even possessing perfect technology, this reality would remain. But let's suppose you are willing to accept this. Let's suppose you develop a spacecraft capable of traveling at 90% of light speed using antimatter or some other miraculous technology. Would you be free from dangers? Negative. Now you face another lethal danger, interstellar dust. The space between stars is not absolutely unpopulated. As I mentioned previously, there exists approximately 1 hydrogen nucleus per cubic centimeter on average. That seems extremely scarce, and it is, but when you travel at speeds close to light speed, even these dispersed particles become dangerous. Here is the reason. At relativistic speeds, even tiny particles carry a colossal amount of kinetic energy. When they impact your spacecraft, it is like being bombarded by high-energy cosmic radiation. A single hydrogen nucleus impacting your spacecraft at 90% of light speed carries approximately the same energy as a projectile fired by a rifle. Now visualize your spacecraft receiving the bombardment of billions of these projectiles per second. The structure of your spacecraft would deteriorate rapidly. Even worse, the impacts would generate secondary radiation, triggering a cascade of high-level energetic particles inside the spacecraft. This radiation would be lethal to any crew, even with robust shielding. Safeguarding humans from this radiation would be extremely complicated. Some have proposed using an electromagnetic shield comparable to Earth's magnetic field that safeguards us from solar storms to repel charged particles. But interstellar space also harbors particles without charge that would not be repelled by electromagnetic fields. And at truly extreme speeds, even photons, light particles, carry sufficient energy to become lethal. The light from stars approaching you would experience blue shift, transformed to higher frequencies. Due to your speed, visible light would mutate into ultraviolet light or even X-radiation. You would be navigating within a radioactive hurricane generated by your own speed. Then there are the larger dust fragments, the microparticles that sporadically float through interstellar space. A particle the size of a grain of sand impacting your spacecraft at 90% of light speed would have the force of a small atomic detonation. A single one of these collisions could annihilate your spacecraft instantly. Identifying and dodging these fragments would be practically unattainable. You would be moving with such rapidity that reacting would be unfeasible. By the time you identify a fragment in your trajectory, you would have already collided with it. You would require some class of frontal shielding on your spacecraft, something disposable that absorbs the collisions and safeguards the rest of the spacecraft. But this shielding would have to be colossal and perpetually substituted or restored. Some designs propose multiple layers of shielding, fundamentally spaced armor that vaporizes incoming particles before they contact the main structure. But this incorporates considerable mass, which demands more energy to accelerate. The faster you try to travel, the worse the radiation and dust dilemma intensifies. It is another elementary barrier. Another demonstration that the cosmos is not configured for living organisms to cross it at relativistic speeds. Now let's talk about something that could look like an alternative, multi-generational spacecraft. If the journey turns out to be excessively long for a single human lifetime, why not dispatch a spacecraft sufficiently enormous to sustain a population for generations? The first generation departs from Earth, lives out their lives aboard the spacecraft, procreates, and eventually dies. Their descendants mature on the spacecraft, never having experienced Earth, and ultimately procreate their own offspring. This cycle persists for decades or centuries until the spacecraft finally reaches its destination. The final generations settle the new planet, fulfilling the mission initiated by their ancestors long ago. Multi-generational spacecraft have been a fundamental pillar of science fiction for decades, and in theory there is no physical law that prevents them. They do not require exotic physics or unattainable energy sources. They merely require an extremely colossal spacecraft with self-sufficient life support systems and a population committed to spending their entire lives in transit. But when you analyze the details, the obstacles become devastating. First, consider volume. To sustain a human population across multiple generations, you need abundant space. Humans do not function well when confined to restricted environments for extended periods. Research into prolonged confinement, such as Mars simulations, reveals that even small groups of highly trained individuals struggle with the psychological consequences of enclosure after only a few months or years. Now imagine entire generations being born, living, and dying within the same sealed environment. They never experience open skies, oceans, jungles, or mountain ranges, none of the experiences that humans have evolved to find comforting and stimulating. To prevent severe psychological disorders, you would need to create an environment that feels spacious and diverse. This means your spacecraft would need to be gigantic, possibly kilometers in diameter, with multiple habitats, green zones, and perhaps even artificial bodies of water. The larger the spacecraft, the greater its mass, and the more energy is required to accelerate it. The mass increases rapidly. A multi-generational spacecraft could weigh millions of tons, possibly even more. Accelerating such a structure to 10% of the speed of light would require amounts of energy that eclipse anything our civilization is currently capable of generating, even assuming fusion or antimatter. The energy demands could prove unattainable. Then there is the problem of life support. Humans require atmosphere, water, nutrients, and waste processing. On short journeys you can carry these supplies or recycle them imperfectly, but on multi-generational journeys you require nearly perfect closed-loop systems. Every atom of carbon, nitrogen, hydrogen, and oxygen must be recycled repeatedly for decades or centuries without significant losses. From our experience with the International Space Station and other missions, we know that current life support systems are not perfect. There are leaks, inefficiencies, and the buildup of contaminants. Over time, these problems intensify. On a journey lasting decades or centuries, even tiny inefficiencies eventually consume your resources. You would need self-sustaining ecosystems, essentially a miniaturized Earth ecosystem inside the spacecraft. Plants to generate breathable atmosphere and nutrients, microorganisms to break down waste, water systems for recycling. We have attempted to create sealed ecosystems on Earth, such as projects like Biosphere 2, and they have not achieved complete success. Maintaining a balanced and stable ecosystem over long periods is extraordinarily difficult. Any imbalance, any species that dies out or proliferates uncontrollably can destabilize the entire system. On a spacecraft, you cannot simply open a hatch to get more breathable air or import supplies if your crops fail. You are absolutely isolated. There is also the problem of maintenance and repair. Over decades or centuries, machinery degrades, components fail, computers require updates, and structures develop microfractures. On Earth, we can manufacture replacement parts, import materials, and consult specialists. On a multi-generational spacecraft, you must be entirely self-sufficient. You need to carry every spare part you might possibly require, or you need onboard manufacturing capabilities to produce new ones. This implies workshops, raw materials, tools, all of which add mass and complexity. And you need people with the skills to use those tools: engineers, technicians, scientists. But how do you preserve that knowledge across generations? What if a field of specialization disappears because no one in a particular generation chooses to study it? What if critical information is damaged and no one remembers how to repair an essential system? Then there is the problem of governance. How do you manage an isolated population for generations? What happens if political or social tensions emerge? On Earth, dissatisfied individuals can relocate, form new communities, or rebel. On a spacecraft, you are trapped. There is nowhere to go. Tensions could escalate into violence, potentially jeopardizing the entire mission. You need stable social structures capable of lasting centuries, preserving motivation, a sense of purpose, and cooperation from generation to generation. That is something no human society has achieved on Earth for such extended periods without significant transformations and upheavals. There is also the question of motivation. The first-generation volunteers for the mission. They understand the purpose and believe in the goal. But what about subsequent generations? They were born on the spacecraft with no alternative. They have never experienced Earth. The target planet is no more tangible to them than a story. Why should they care about completing an expedition begun by people who died long before they were born? What happens if they decide they do not want to continue? What if they want to return to Earth, head somewhere else, or simply stay where they are? There are also genetic problems. A small population on a multi-generational spacecraft would face inbreeding. Over time, this leads to genetic disorders. You need a sufficiently large founding population to preserve genetic diversity, certainly several hundred or even thousands of individuals. But the larger the population, the more enormous the spacecraft must be, the more resources it requires, and the more energy is needed to accelerate it. The ideal multi-generational spacecraft would essentially be a small, self-sufficient planet, a colossal structure capable of supporting an entire civilization indefinitely. Building such a thing would require resources and technology far beyond our current capabilities, and you would still have to accept colossal risks. A single catastrophic point of failure, a mechanical breakdown, a radiation event, an epidemic, could wipe out the entire population. There is no rescue, no assistance. You are isolated in the darkness between the stars. Given these difficulties, some have proposed a different alternative: cryogenic hibernation. Instead of keeping a crew alive for centuries, why not freeze them? You suspend their biological functions, place them in some kind of stasis, and reactivate them when they arrive at their destination. In this way, you do not need colossal multigenerational spacecraft or self-sustaining ecosystems. You only need to preserve the frozen organisms and keep the spacecraft's critical systems operating. The crew experiences the journey as a blink of an eye. They fall asleep on Earth and wake up in a new star system. It sounds perfect, right? The problem is that cryonics, as this technology is called, does not currently work, at least not in the way we would need for interstellar travel. We can freeze cells, tiny tissues, and even some organs and revive them with mixed results. But freezing an entire human organism and reviving it without damage is something we have never achieved. The main problem lies in the formation of ice crystals. When you freeze biological tissue, the liquid inside cells forms ice crystals. These crystals are sharp and rigid, and they puncture cell membranes, destroying the delicate structure of the cells. When you attempt to thaw the tissue, you end up with a cellular catastrophe. The cells are shattered, their membranes are perforated, and their organelles are damaged. The tissue essentially turns into mush. There are techniques known as vitrification that attempt to prevent the formation of ice crystals. Instead of freezing, you transform the tissue into a glass-like state using cryoprotectants, chemical compounds that prevent crystallization. This works better than simple freezing, but it has its own problems. Cryoprotectants are toxic at high concentrations. You must perfuse the entire organism with these chemicals, replacing the blood and tissue fluids. Then you must cool the organism extremely rapidly and uniformly, which is exceptionally difficult to do for something as large as a human body. Different parts of the body cool at different rates, leading to thermal stress and fracturing. Even if you successfully vitrify an organism, storing it for decades or centuries presents further challenges. You must maintain extremely low temperatures, typically using liquid nitrogen at -196 degrees Celsius. Any temperature fluctuation, any warming, even slight, can initiate crystallization or cause fracturing. And then there is the process of reanimation. You must thaw or devitrify the organism uniformly and rapidly, remove the toxic cryoprotectants without damaging the tissues, restart the heart and respiration, and somehow restore brain function without loss of memory or personality. Today, this is completely beyond our reach. Certain companies offer cryogenic preservation services for the deceased, freezing their bodies or just their brains in the hope that future technology will be able to revive them. However, this is based on belief, not on verified science. No cryopreserved mammal has ever been successfully revived, let alone a human being. Even assuming that future technology will solve these problems, other complications remain. During a journey lasting decades or centuries, the spacecraft systems must operate flawlessly. A failure in the cooling system and the crew would thaw prematurely, or worse, rot. You need energy sources that can last centuries, monitoring systems that never fail, and probably some form of artificial intelligence or computational systems capable of managing the spacecraft and responding to crises without human involvement. This raises another question. If you have AI or computer systems sophisticated enough to run an interstellar spacecraft for centuries, why send humans at all? This brings us to another proposal: robotic explorers. Instead of sending humans, we send machines. Robots do not need oxygen, food, water, or a comfortable temperature. They can withstand radiation that would kill a human. They can be engineered to endure for centuries with minimal maintenance, and if they malfunction or are destroyed, it represents a scientific loss rather than a human catastrophe. In reality, robotic explorers constitute our most promising near-term option for interstellar exploration. We have already sent them beyond our planetary system. The Voyager missions, launched in 1977, are currently traveling through interstellar space, more than 20 billion kilometers away. They continue to transmit data after nearly half a century. They are evidence of what human engineering can achieve. However, the Voyagers travel slowly at only about 60,000 kilometers per hour. At that speed, they would need more than 70,000 years to reach Proxima Centauri. To explore other star systems within a reasonable time frame, we need much faster probes. Breakthrough Starshot is an initiative that proposes to achieve exactly that. The concept is to build tiny probes, each weighing only a few grams, and propel them using Earth-based laser beams. You attach a photonic sail, a thin, reflective membrane, to each probe. Then you aim a powerful array of lasers at the sail. The force of the laser radiation pushes the sail, accelerating the probe. Projections suggest that these probes could be accelerated to 20% of the speed of light, fast enough to reach Proxima Centauri in roughly 20 years. This would be transformative. You could launch a probe today and, within your lifetime, receive data and images from another star system. You could observe exoplanets up close, analyze their atmospheres, search for signs of life, all without sending humans. But Breakthrough Starshot faces its own barriers. First, you need to build a laser array capable of generating gigawatts of power, focused with astonishing precision onto a tiny sail that is rapidly accelerating. This requires advances in laser technology, adaptive focusing systems, and energy generation. Then you need to build the probes themselves. They must be extremely lightweight, just a few grams, yet still carry cameras, detectors, computing systems, and transmitters. They must survive the acceleration phase, endure a 20-year journey through interstellar space, and still have enough power to transmit data back across trillions of kilometers. This is miniaturized engineering pushed to its limits. Then there is the transmission problem. At a distance of 20 light-years, an electromagnetic signal takes 20 years to return. You launch your probe, wait 20 years for it to arrive, and then wait another 20 years for the data to come back. That is a 40-year commitment from launch to first results. And when the signals arrive, they will be extremely faint. You need enormous arrays of ground-based antennas to detect them. Despite these obstacles, robotic explorers are feasible. They do not violate any physical laws. They are extraordinarily challenging engineering projects, but not unattainable. If humanity commits the resources and dedication, we could send probes to nearby star systems in the coming decades. However, note that we are talking about tiny probes, not crude spacecraft. We are talking about exploration, not colonization. Probes can take photographs, collect data, and search for life. They cannot establish settlements, return samples, or provide an alternative refuge for humanity if something happens to Earth. For that, you need humans, or at least some means of transporting life and technology to found a settlement. And that is precisely where the fundamental constraints become evident. Let us now talk about something that sounds like speculative fiction but is actually grounded in real physics: wormholes and warp drives. A wormhole is a shortcut through space-time, a tunnel that connects two distant locations in the universe. In theory, if you could create or find a wormhole, you could enter one end near Earth and emerge from the other end near Proxima Centauri almost instantly. You would not be traveling faster than light. You would simply be taking a shortcut. The concept arises from Einstein's general theory of relativity, which describes how gravity warps space-time. Certain types of distortions, at least mathematically, can produce these tunnel-like configurations. The problem is that wormholes, if they exist at all, would likely be incredibly fragile. They would collapse as soon as you tried to use them. To keep a wormhole open, you would need something called exotic matter with negative energy density. This is not antimatter. It is something even more mysterious, matter with repulsive gravitational properties. We have no evidence that exotic matter exists in usable quantities, if it exists at all. Some scientists believe that the Casimir effect, a quantum phenomenon, can produce negative energy densities on extremely small scales. However, scaling this up to macroscopic levels, enough to create a traversable wormhole, is completely beyond our technological capabilities and possibly beyond what the laws of physics allow. Even if you could create a wormhole, it would need to be stabilized and positioned correctly, with one end near Earth and the other near your destination. How do you transport the far end to your destination? You would have to move it there at conventional subliminal speeds, which brings us right back to the original dilemma. Wormholes are theoretically fascinating, but in practice they are far from being a usable alternative. They may as well be magic. We cannot build them, we do not know whether they can exist, and we have no way to stabilize or control them even if we could create them. Then there is the warp drive. Popularized by Star Trek, but in fact grounded in a real physical concept proposed by the scientist Miguel Alcubierre in 1994. The idea behind the warp drive is to distort space-time around your spacecraft, compressing space in front of you and expanding space behind you. The spacecraft itself remains inside a bubble of flat space-time, not moving through space in the conventional way. Instead, space itself moves around you. Since space can expand or contract faster than the speed of light, there is theoretically no speed limit. You could travel faster than light without violating relativity, because technically you are not moving through space faster than light, you are moving space itself. It sounds incredible, right? The problem is that, like wormholes, the Alcubierre warp drive requires exotic matter with negative energy density. The energy scales involved are astronomical. Early estimates suggested that you would need more energy than is contained in the entire mass of the observable universe. Later research has reduced the energy requirements, but they are still vastly beyond anything we could possibly generate. And that is only the beginning. Creating and maintaining a warp bubble would require precise control over space-time itself. You would need to generate extremely intense and highly focused gravitational fields, something we have no idea how to do. The bubble would have to move without destroying the spacecraft inside it. There are concerns that anything inside the bubble would be unable to communicate with the outside, making it impossible to steer or control the bubble once it is in motion. And when you finally shut down the warp drive, all the energy accumulated in front of the bubble could be released catastrophically, potentially annihilating your destination in a burst of radiation. These are deep problems, not merely engineering challenges. We are talking about physics we do not fully understand, phenomena we have never observed, and technologies that may be fundamentally unattainable. Warp drives and wormholes are theoretically captivating, but in practice they offer no real solution to our interstellar travel dilemma. So here we are, examining all the options. Chemical rockets are far too slow. Nuclear fission gets us to only a few % of the speed of light. Fusion, if we manage to make it work, might reach 10 or 20%. Antimatter, even if we could produce and store it, might reach 50 or 90% of the speed of light, but with enormous technical challenges. Multi-generational spacecraft require colossal resources and technology with immense social and biological risks. Cryonics does not work, at least not yet. Robotic explorers are our most promising option, but they cannot establish colonies. Wormholes and warp drives are speculative and likely unattainable. Do you see the pattern? Every potential alternative faces fundamental barriers. We are not talking about problems that can be solved with better materials or faster computers. We are talking about limits imposed by the laws of physics, the scale of energy available in the universe, and the very nature of space and time themselves. Now let us consider another dimension of the problem, the destination. Suppose we somehow overcome all these obstacles. We build a spacecraft, accelerate it to a significant fraction of the speed of light, and arrive at Proxima Centauri after decades of travel. What do we find there? Proxima Centauri is a red dwarf, a class of star known for its violent stellar activity. It emits powerful flares, bursts of radiation that could sterilize any nearby world. Proxima Centauri b, the exoplanet that orbits within the star's habitable zone, is much closer to its star than Earth is to the Sun, because red dwarfs are far dimmer. This proximity means the planet is likely tidally locked, permanently showing the same face to its star, just as the Moon always shows the same face to Earth. One hemisphere of the planet would be perpetually scorched, the other perpetually frozen. There might be a narrow band between the two where conditions could be tolerable, but this is far from certain. We also do not know whether Proxima Centauri b has an atmosphere. The intense radiation from stellar flares may have stripped it away long ago. Without an atmosphere, the planet is uninhabitable, at least on the surface. There would be no breathable air, no atmospheric pressure, and extreme temperatures. Even if an atmosphere exists, it could be toxic, composed of carbon dioxide, methane, or other gases that humans cannot breathe. We would need to examine a world meticulously before sending settlers, yet doing so from Earth with telescopes has limitations. The best instruments we possess can only confirm that the world exists and calculate its size and orbit. Determining its atmosphere, surface characteristics, whether it contains liquid, whether it harbors organisms, requires close-range missions, explorers capable of studying the world in detail. And such missions require decades to reach their destination and decades for the information to return. Thus, even identifying a suitable target is a long and complex process. And Proxima Centauri is the nearest star. The vast majority of the remaining stars are much farther away. To locate a truly habitable world, one with an atmosphere, liquid, suitable temperatures, stable geology, we may need to examine dozens or hundreds of light years away. The number of stars within 10 light years of the Sun amounts to only a few dozen. Many of them are red dwarfs like Proxima Centauri. Some are binary stars or multiple systems where stable planetary orbits are problematic. Some are excessively old or excessively young. Finding a world truly analogous to Earth, one where humans could live without extensive modifications or sealed habitats, may require surveying hundreds of stellar systems. And each of those systems lies light years away. The distances and timescales are simply overwhelming. Then there is the question of motivation. Why would we want to travel to the stars in the first place? There are many reasons people cite: scientific curiosity, the desire to explore, the search for extraterrestrial organisms, the aspiration to spread human civilization beyond Earth. There are also pragmatic arguments. Earth faces multiple existential threats: climate change, nuclear conflict, pandemics, asteroid impacts, megavolcanic eruptions. Having settlements on other worlds could serve as a contingency safeguard for the human species. If something devastating happens to Earth, humanity could endure elsewhere. This is the eggs argument. Do not put all your eggs in one basket. It makes sense in theory. However, establishing self-sustaining settlements in other stellar systems requires a level of resources and technology that is currently far beyond us. Consider what would be required to transform Mars, our nearest and most Earth-like planetary neighbor, into a habitable location. Mars lacks a magnetic field, so galactic radiation bombards the surface. It has an extremely thin atmosphere, predominantly carbon dioxide, with a surface pressure less than 1% of Earth's. There is no liquid water on the surface. Temperatures can drop to -125 degrees Celsius during the night. The soil contains perchlorates, chemicals lethal to humans. To live on Mars, you would need sealed habitats, life support systems, radiation shielding, indoor food production, water extraction and purification, oxygen generation, and waste management. Fundamentally, you would need to build and maintain a synthetic Earth-like ecosystem inside protected structures. This is achievable, though complex, because Mars is nearby. We can send supplies and equipment from Earth. Travel times are months, not decades. Communication delays are minutes, not years. If something fails, there is a chance of rescue or resupply. Now imagine doing the same on a world light years away. There is no resupply, there is no rescue. The settlement must be completely self-sufficient from the outset. This means transporting not only people, but also all machinery, tools, materials, seeds, animals if necessary, knowledge, and technology to build and sustain a civilization from scratch. The mass involved would be enormous, far beyond what any propulsion system we have studied could reasonably deliver. And all of this assumes that you find a world worth settling, one that does not kill you with its atmosphere, radiation, geology, or native biology. One might argue that if we possess the technology to travel between the stars and establish settlements on hostile alien worlds, then we surely possess the technology to make Earth habitable no matter what happens. If we can build self-sustaining habitats on other worlds, we can build them on Earth, even under the most catastrophic conceivable conditions. It is far easier to live underground or under domes on Earth than to travel light years to live underground or under domes on another world. This is a crucial point. Interstellar colonization is not a pragmatic short or medium-term response to the existential risks we face. It does not save humanity from climate change, nuclear war, or pandemics. By the time we have the technology and resources to establish interstellar settlements, If we ever do, we will also have the technology to make Earth habitable regardless of circumstances. Thus, the pragmatic motivation, the contingency safeguard, collapses under rigorous analysis. What about scientific curiosity? The desire to discover and to understand. These are noble. Certainly, humans are inherently explorers. However, exploration can be carried out by automated probes, as we have discussed. It does not require sending humans. And from a scientific perspective, sending humans is less productive than sending probes. Humans are fragile, require vast resources, and have complex needs. Machines do not. For every unit of money spent on sending humans, you could likely send 100 automated explorers. So what remains? The romantic aspiration to spread human civilization to the stars, to become an interplanetary, interstellar, perhaps even intergalactic species. It is an inspiring vision that has fueled speculative fiction for more than 100 years. Yet when confronted with the harsh and unforgiving reality of physical laws, the immensity of the cosmos and technological constraints, that aspiration increasingly appears to be a mirage. This does not mean that we should never attempt it. Human history is full of achievements that once seemed impossible until they were realized. However, it is crucial to be transparent about the obstacles we face. Interstellar travel is not merely a difficult technical problem. It is possibly the most monumental challenge humanity could undertake, requiring revolutions in physics, engineering, biology, and social sciences that could take centuries or millennia, if they are feasible at all. Now let us speak of something more existential. Suppose that by some means we solve all these problems. We build spacecraft capable of traveling at relativistic speeds. We find habitable worlds and establish settlements. What does this mean for our human essence? At speeds close to that of light, time dilation means that settlers age more slowly than people on Earth. If you send a settlement to a world 50 light-years away, traveling at 90% of the speed of light, they might arrive in about 55 years as measured on Earth due to acceleration and deceleration. Yet for them, because of time dilation, it might feel like only 20 or 25 years. They step down onto their new home only slightly older than when they left. But on Earth, more than half a century has passed. Everyone they knew is dead or elderly. Social structures have changed. Technological advances have progressed. If they try to communicate with Earth, transmissions take 50 years in each direction. A single exchange of messages requires a full century. The settlers are no longer part of Earth's civilization. They are an independent offshoot, evolving on their own. Over time, under the influence of a different environment, perhaps a different gravity, a different atmospheric composition, different light cycles, they would develop biological variations. After thousands of generations, they might become unrecognizable as humans by our current understanding. They could transform into a different species. This could happen even without interstellar expansion. If we establish settlements on Mars, on Jovian moons, in asteroid belts, each will evolve differently. But the separation and isolation of interstellar expansion make the rupture far deeper and more permanent. An interstellar settlement is not merely an extension of humanity, it is the birth of a new evolutionary trajectory. There is also a profound contradiction here. If interstellar travel is so difficult for us, it is probably just as difficult for any other civilization. This could explain the Fermi paradox, the question of why we have not detected evidence of intelligent extraterrestrial life. If there are billions of potentially habitable worlds in the galaxy, and if life is common, then there should be many civilizations out there. Some should be far older and more advanced than we are. They should have colonized the galaxy countless ages ago. We should detect their transmissions, their megastructures, their technology. Yet we detect absolutely nothing. The cosmos seems silent. Perhaps the explanation is that interstellar travel is simply too hard. Even advanced civilizations cannot overcome it. The laws of physics are universal for everyone. If you cannot travel faster than light, and if the distances are so enormous, then each civilization remains confined to its home star system, perhaps exploring nearby stars with probes, but never truly spreading across the galaxy. This would imply that the galaxy is filled with isolated civilizations, each alone in its tiny spatial bubble, unable to communicate or interact with one another because of the immense separations involved. It is a bleak picture, but it may be our reality. Or perhaps civilizations do not last long enough. There may be some filter, some obstacle that civilizations face that most fail to overcome. It could be technological, such as developing weapons capable of destroying entire worlds. It could be environmental, such as climate upheaval or other ecological catastrophes. It could be social, such as political turmoil or economic collapse. If civilizations tend to destroy or unravel themselves before developing interstellar travel, then the galaxy would be filled with ruins rather than active civilizations. There is also the possibility that interstellar travel is simply undesirable. Perhaps advanced civilizations conclude that it is not worth the effort. Perhaps they turn inward, creating virtual realities, exploring computational universes, or transferring their consciousness to inorganic substrates. Perhaps they discover ways to satisfy all their needs without requiring physical expansion. This is speculation, of course. We do not know why we do not detect extraterrestrials, but the difficulties of interstellar travel certainly contribute part of the explanation. Perhaps we are all simply trapped, each civilization on its own spatial archipelago, separated by oceans of empty space that are practically impossible to cross. Let us return to Earth, to our tiny blue sphere, orbiting an ordinary star in an unremarkable galaxy. From our perspective, the cosmos is almost infinitely vast. There are approximately 200 billion trillion stars in the observable universe, each potentially accompanied by worlds. The distances between these stars are so immense that light, the fastest entity in the universe, takes years, centuries, millennia to travel between them. And yet, we remain here on this single world, looking outward and wondering whether we will ever reach those other worlds. The answer, based on everything we know, is probably no. At least not in any foreseeable future, not with technology we can realistically conceive, not with physics as we understand it. The obstacles are not merely technical, they are fundamental, woven into the very fabric of space-time. The speed of light is an absolute limit. You cannot travel faster, no matter how much energy you have. And at that speed, the distances are devastating. The energy required to propel spacecraft to relativistic velocities exceeds what our civilization can generate, perhaps exceeds what any civilization could generate without access to resources on a stellar or galactic scale. The dangers of interstellar space, radiation, dust, the need for shielding and life support add layers of complexity that may be insurmountable. And all of this assumes that you find a destination worth the effort, a world where you can truly live, which in itself is an enormous assumption. I am not saying that we should never try. I am not saying we should abandon the aspiration to explore the cosmos. But we must be pragmatic about what is feasible. The grand exploration of the stars, the idea of humanity spreading across the galaxy, populating thousands of worlds, encountering alien civilizations, this may remain fiction forever. The reality is that we are confined to this tiny fragment of the universe, not because we lack ambition or ingenuity, but because of the immutable laws of physics. Perhaps that is not a bad thing. Perhaps we should learn to value the home we have, to protect it, to preserve it, to ensure that it remains habitable for future generations. Perhaps the lesson of the cosmos is not that we must conquer it, but that we must understand our place within it. We are a young species on an ancient world, orbiting an ordinary star in a galaxy filled with hundreds of billions of other stars. We are small, fragile, and likely alone for a very, very long time. If other civilizations exist, they are so distant that we may never communicate with them, much less visit them. And that is acceptable. The universe owes us nothing. It was not made for us. We simply exist within it for a fleeting blink of cosmic time, trying to give meaning to our existence. So why is it unattainable for humans to travel beyond the solar system? Because the universe is vast beyond comprehension. Because the distances between stars are so immense that even light, traveling at the maximum conceivable speed, takes years to cross them. Because the energy required to propel a spacecraft to significant fractions of the speed of light exceeds our capacity to generate it. Because the hazards of interstellar space, radiation, dust, the cold vacuum, are hostile to life. Because we have no way to sustain humans for the decades or centuries such journeys would require. Because building multigenerational spacecraft or developing workable cryonics exceeds our current technology and possibly any future technology. Because potential destinations are unknown, possibly uninhabitable, and would take generations just to discover. Because the laws of physics, special relativity, thermodynamics, conservation of energy, all conspire to make interstellar travel extraordinarily difficult, if not impossible. It is not that we are insufficiently intelligent or ingenious. It is that the universe is arranged in a way that keeps things apart. And perhaps that is the ultimate lesson. We live in a universe designed for isolation. Stars are separated by light years of emptiness. Galaxies are separated by millions of light years. The observable universe is bounded by the speed of light and the expansion of space. Even if we could travel at the speed of light, which we cannot, much of the universe would remain forever unreachable, carried beyond the cosmic horizon by the accelerating expansion of space itself. We are trapped in our tiny corner of the cosmos, not by choice, but by design. And perhaps that is something we must accept. The universe is vast, beautiful, and mysterious, but most of it lies beyond our reach. We can study it, we can observe it, we can send robotic explorers if we are fortunate, but going there ourselves, walking on the shores of alien worlds, gazing at strange suns, that may remain an aspiration forever. Tonight we have traveled through the barriers that prevent us from reaching the stars. We have examined the impossible distances, the overwhelming energy demands, the deadly hazards, and the fundamental constraints imposed by physical law. This is not an optimistic story. It does not end with humans exploring the galaxy. It ends with the understanding that we are, and likely will always be, confined to this tiny blue world, and perhaps to our solar system if we are lucky. Yet there is beauty in that understanding. It reminds us that Earth is precious. It is the only home we will ever have. And instead of dreaming of escape to the stars, perhaps we should focus on making this world the best place it can be. Thank you for joining me on this journey through the limits of what is possible. If you found this exploration valuable, a like or a subscription would mean a great deal and help the channel continue creating this kind of deep content. Good night, and may you find peace in knowing your place in the cosmos, however small it may be.